We'll wait for a few moments, then we'll start at exactly at 6 o'clock. So it's sharp 6 p.m. and we'll just start with the lecture. Hope I'm audible and my screen is visible. So welcome to this live interaction session for week 6 for NPTEL course in nanobiotechnology enabled point of care devices. The course code is NOC 24G23. The course instructor is Professor Gurchan Datta, School of Medical Sciences and Technology, Indian Institute of Technology, Kharagpur. My name is Amay Dukle. I am Prime Minister's Research Fellow in Department of Mechanical Engineering, IIT Tirupati. I will be helping you with this problem solving session. So before we begin, some of the just some formalities. So this live session is to boost your performance. It is not compulsory, but it is highly encouraged. We request you to be respectful in chat. In case you have any questions, you can unmute yourself at any time and just ask the question. You can also ask the questions at the end of the session. Videos will be uploaded on YouTube. You can directly go through this link for my channel, or you can go through the public Google Doc that has been uploaded on the NPTEL page. So moving to the what is the session plan for this session is we'll first discuss the practice assignment questions, and then we'll move to the question and answer session. So hope I am clear with this. So moving to the course outline. So this is a 8-week course. We are currently in the week 6. We will be. This is mainly about design of point of care devices. How the design is happening is what is there in this week's content, and also there are some like um, as per the syllabus, it is supposed to be how new detection system works, how biosensors to mobile devices, how wearable biosensors and disposable and self-powered point of care devices work. But in this week, mostly if you go as per syllabus, it is more about designing of the new systems. So as sir said, designing of new system is actually a PhD in itself. There are many people who are actually doing their PhD in that domain. So it is very complicated to learn these things in one go, but we will try to solve your doubts as much as possible. So since we have done with the basic formalities, we'll start with the practice assignment. So this is the first question. So basically in this this is a schematic which has been given, and the question is what is the role of NaBH4, that is sodium borohydrate, in the above scheme of reaction. So whether it does surface pretreatment, reduction in surface nanoparticles, functionalization of surface adsorbed aptase, or does nothing. So just before you can guess something, I'll just give you an overview of what is happening in this reaction. So basically we have an Indian tin oxide substrate. So then that has been functionalized with the aptase. So basically you have an surface that has so in order to uh, attach the antibodies to the surface, first you need to activate the surface. So basically aptase are what the aptase are doing is they are activating the surface, and they are making the surface hydrophilic or in nature, so that the we can uh, make the whatever we need to deposit. So whether we need to deposit the proteins or antibodies, we are modifying the surface in that way using aptase. So then what we are doing is, since we have got the surface activated, so we have got the amine group, so then what we do is ferrocyanine carboxylaldehyde and NaBH4, we use it to change the functional group. So we have already we activated the surface, then we have some functional group on this surface, then we modify those functional groups using the NaBH4 ferrocyanine carboxyaldehyde reaction. Then we put streptavidin. Streptavidin is a protein. So after that protein, why is streptavidin being used in this reaction is basically streptavidin has 4 binding site for biotin antibodies. So we put so now in the first section, we can say we got the surface, we activated the surface, then we functionalized the activated functional groups which we needed, so that we can attach streptavidin to it. Then we attach streptavidin to it. Then after the streptavidin is attached, we attach biotin antibody, that is a primary antibody, to the streptavidin. Then in the next phase, the target antibody is coming and attaching to the streptavidin. Then we have a secondary antibody that is labeled with ALP, that is attaching to the primary antibody. So I hope you are able to understand the scheme of reaction in this. You are able to understand what the designer wants to do in this. So what he is doing is he is getting the surface substrate, the substrate for the sensor. He's activating it so that he can get the protein he wants. On that he can deposit the protein he wants on the surface. So first he's activating it, he's getting the amine groups, then he's functionalizing those amine groups so that he can get what he wants. So first activating, then changing the activating surface so that what you can deposit what you want, then you deposit what you want, then you put the antibodies so that the antibodies have a substrate to have a surface to be binded, so that they can attach directly to the to that protein. Then you detect the primary antibody, and then you just put the secondary antibody that is labeled. So this is the overview of the sensor per se. So this is something which you need to understand. So what the designer has done. So now after I explained all of this, what do you think will be the main purpose of that NaBH4 in this reaction? So is it surface pretreatment? No, because it is coming in the second step. In the it is not coming with the aptite, so surface pretreatment is not there. Then reduction of surface nanoparticles. NaBH4 is widely used in enhancing the electrocatalytic activity of gold nanoparticles, but in this reaction we don't have any gold nanoparticles, so answer B is invalid. So in the third reaction, basically what it is doing is NaBH4 is functionalizing the amine groups in the aptase. So that is what it is doing. So now you can just tell me what do you think will be the answer, whether it is answer is C or D. So So any guesses whether the answer is C or D? I have shortened I have basically explained the entire sensor to you, explained the sensor design to you. I have even played 50-50 with you and given you eliminated two answers for you. So can you just uh, tell me what the answer will be, whether it will be C or D? Okay, so the answer is C. It is basically functionalizing the surface adsorbed aptase. So basically, it is reacting with the amine groups in aptase, and it is basically then it is allowing the ferrocin formaldehyde, ferrocin carboxyaldehyde to react with the functional group with the amine groups, and so that it can get a suitable site for streptavidin. So the answer is answer C. Any questions? So I don't see any questions in the chat. So in case you have any questions, please unmute yourself. So moving to the next question. So in this is the same reaction which is there. So here now what they are asking is whether what will be the change in RCT after addition of streptavidin. Decrease in value remains same, increases very slightly. So RCT is basically related to surface level charges. So if there are very heavy what you can say very heavy antibodies or very heavy proteins that come near the surface electrical properties also changes, so the resistance changes, so the charge transfer also changes, so that is the resistance to charge transfer. So because of heavy bodies, the charge transfer gets slowed down. So what do you think will be the answer for this? Okay, so the answer is C. It increases. So as I said, streptavidin is very heavy in nature. So when it when it is put on the surface, what happens is it increases the load per se on the surface. So when see, imagine the electron flow as a flow of water. So if you put any heavy body in the path of water, even if the so imagine just the electron is moving on so just to imagine what I'm saying is, just imagine you have a plate, you have a water flowing on it, and then you just put some heavy objects on that. So what will happen is basically the flow of water will get interrupted. So same thing is happening. Basically, the electron is moving on the substrate, but because of streptavidin, there is obstruction to the flow of electrons. So that is basically increasing the charge transfer resistance in the sensor. So that is how you can imagine what is going on in this scenario. So do you have any questions? Since the setup is the same, I have not explained it again. If you want me to explain the setup again, please let me know. You can unmute yourself, or you can put your questions in chat. I'm monitoring both. Okay, fine. I'll move to the next question. So basically, in the third question. Third question, what they are asking is what is the role of secondary antibody in the above scheme. So as I said, they are first activating the surface, then they are functionalizing the surface, then they are putting the protein as a binding site for the primary antibody. Then they are binding the primary antibody, that is the detection antibody. Then they are adding the target antibody. Then they are adding the secondary antibody. So in this, why would a person add the secondary antibody? Whether it will be improve the signal to background ratio, whether it will be to used to prevent non-specific binding of the surface, for stabilizing the biotin, or for stabilizing the target antibody. So this is basically, it is how you understand it. So basically what here it is what is happening is, it is so just go let's go with the elimination options. So what is happening is, let's go from go with like option D, use for stabilization of target antibody. Yes, this can be possible, but then in that case it will only be an antibody, there will not be any labeling element. So ALP is a alkaline phosphatase, is a it's a redox, means it is supposed to actually do a redox reaction in this um, uh, in this sensor setup. So basically, if it is used for redox reaction in this setup, it is not technically used. It can be used for stabilization. Stabilization can be a purpose, but since it's a labeled antibody, you can just think of it that labeling is basically in you can go through week 2 or week 3 lectures. In that, basically what is happening is, to reduce the signal, to improve the signal to background ratio is why we are doing the labeling. So when you have a labeled secondary antibody, you can think of it as that way. So rather than eliminating, I would say go with this approach. Basically, since it has a ALP labeling on the secondary antibody, you can see that there will be a redox reaction that will happen on in the entire sensor setup, and that will increase the signal ratio. So that is why we are using the secondary antibody. Because if so, should it not Sachit, whether which question are you talking about? Whether it's 1, 2, or 3? Question number 2. Just a moment. So basically, here as I explained you how what is happening. So charge transfer, basically because of the heavy bodies, because of the heavy antibody, heavy protein. So streptavidin is very heavy in nature. So what is happening here, it will slow down the charge transfer. It will slow down the flow of electrons. As I said, you can imagine in terms of water on a plate. So basically, streptavidin is very heavy. So in case you are doing some functionalization treatment like aptase, or you are putting that, so in that, when the weight of what you are putting is not very high, but obviously there are those molecules on that surface, in that case the resistance increase will be very high. So see, all the organic compounds are non-conductive. That much is it clear? Like, you know about that, right? From the basics, it is like all the organic compounds are non-conductive in nature. So depending on the weight of the compound, the resistance will increase. So basically, you can see that even in a normal case as well. So you use a insulation, a plastic insulation for normal wires. But in case you need very high resistance, you use a ceramic kind of insulation. what do you do with your fuses which you have in your home? So that is what happens. So when the weight increases, the weight of the organic compound increases, the resistance increases. So what is happening is, if you are doing some surface treatment, or if you are doing some like low weight things, like even if you put an antibody which is quite like which has quite lesser weight compared to a protein, the change in charge transfer resistance will be just like the RCT will increase very slightly. But here streptavidin is quite heavy. One streptavidin is weight, in terms of weight, is equivalent to, per se I can say, 2.5 times the weight of a single antibody. So when you are having so many streptavidin, the RCT value will be very high. So the very high doesn't mean like I'm talking about 20-30%. So in terms of biosignaling, the where increases very slightly will be 0.01 to 0.05 or 0.08%, whereas increases will be like 1%, 2%. So in normal case, we say like very slightly we consider 1-2%, but in case of biological signaling, the very slightly is in the 0.01, 0.02% range. So that is why here we are putting it as increases. That's why it is not option D. Do you understand that? Am I clear with that? Okay, so I think I have explained the question 3 also. Just a sec. So because of the labeling element, it is basically inducing some redox reactions on the in the sensor. So that is why it is basically used to enhance the signal to background ratio in this particular sensor. So do you have any questions with this setup? Because the next question moves to another setup. So yeah, so since there is no question, I'll just move to the next setup. So in this, basically what they are doing is, we have surface. It has a electroactive probe that is attached to the surface. So basically they have some uh, organic compound above which there is some electroactive probe. So electroactive probe is basically something that can when it comes near to the surface, there the charge transfer increase. The charge transfer actually happens. So here when so what is happening is, first we have an electroactive probe, and then we are incubating it with the toxin. So because of toxin, the electroactive probe is coming near to the surface, which is leading to increase in the current that is flowing. So this is the entire concept of the sensor. So they are asking what is the concept used. So increase and decrease in the RCT value, proximity dependent electrochemical reaction, antibody antigen reaction, ECC amplification of current. So let's go one by one with the options. So ECC amplification, it requires a redox reaction. So it is a electrochemical chemical redox reaction. So that is not happening. There is no redox reaction happening. You cannot see here in any of the schematic. So that is not happening. Antibody antigen, do you see antibodies and antigen? Antibody is a uh, Y and Y, the sandwich essay. Are you seeing it in this reaction? No, it is not happening. So now this first option is increase and decrease in the RCT values and the proximity dependent electrochemical reaction. So basically it can be like the it is very easy to confuse among both of them. So basically here, but since we are using a electroactive probe, so if there was no electroactive probe and if it was just a antibody, so basically what is happening is, in case of electroactive probe, there is charge transfer happening from the probe to the substrate, and because the distance is quite high, the you are not the current sensed is less, and when the distance reduces, the current sensed is high. So here, so that is why it is a like a proximity dependent reaction. If it was per se in the previous reaction where there was just streptavidin, there was no electroactive substance there. So if there was if there was no electroactive substance there, the so just take this case of toxin in the previous setup, where if we had just put the toxin on in the previous setup. So in the previous setup, since there was no electroactive substance there, what would have happened is the charge would have been flown through the substrate. With the presence of toxin, the charge would have been interrupted, and we would have detected the RCT value. But here what we are measuring is the current value. So that is why the answer is proximity dependent electrochemical reaction. So this is these things are a bit complicated to understand. So just like you can make mistake in the two options. So just try to understand. If you don't understand, just ask me again. Any questions with this? So I don't see any questions, so I'll just move to the next. So in the same setup, basically what they are asking is what is the name of the detection probe in the above scheme: surface absorption reagent, antibody, secondary antibody, aptamer. So this is basically very easy to understand. So basically there are no antibodies or primary or secondary. There is nothing with a Y kind of structure in this entire system. So the antibody, whether primary or antibody, will have a Y kind of system. So it's not there. So antibody and secondary antibody is not the answer. So then we move to surface absorption reagent. So basically in surface absorption reagent, you activate the surface and then you measure the surface level. So that's what was done with aptase in the first setup. So that is what is called as the surface absorption reagent. So here we don't have any reagent per se, and we have a long protein chain that is called as an aptamer that is connected to the electroactive probe. So this is basically an aptamer based system. So this is what the detection probe in this scheme is called. Since it's a protein with a long chain, it is it's the aptamer. That is what it is called. There is like nothing much to explain, but if you have any question, you can ask. So now we move to the next setup. So basically this is a very complicated setup per se. So just to explain what is happening, first basically you have a indium tin oxide substrate. So that is given some binding site. So basically the what you can see in green color, those boxes are binding sites. So basically you need something to put your antibodies on. So you attach you functionalize the surface, attach the binding site, and then you get your antibody. So IG immunoglobulin antibody. So then what you are doing is you are detecting troponin, then you are getting a labeled immunoglobulin antibody, so that has GPDH2. So and you also have AOX enzyme here. So this is a very complex system. Just understand what is happening. You have indium tin oxide substrate, then you have avidin, which is the functionalized site for putting the um, immunoglobulin antibodies. Then you have troponin, which is what we are detecting. Then we have secondary antibody of immunoglobulin that is labeled with GPDH4, with GPDH, and then you have AOX, that is the enzyme here. In the entire thing, we have GPDH, which is having a redox cycling reaction with ruthenium, which is actually leading to electron transfer. So I hope my explanation of the setup is clear. So you have a substrate, avidin, primary antibody, troponin, the detection, the analyte, immunoglobulin, secondary antibody labeled with GPDH4, and AOX enzyme. The redox reaction is of ruthenium. That is what is happening in this case. So you can see that the unbounded antibody, you can see that the reaction is happening in a slow manner. That is because oxygen is it is basically oxygen is taking up the few electrons, and it is oxygen is giving up electrons, and it is converting itself into H2O2. So only thing that is variable in this entire setup is basically uh, oxygen. So because oxygen is coming from outside, it is not a byproduct of any reaction. So what can be a source of variability of sensor for calibration of fixed amount of troponin 1? So whether it's oxygen, hydrogen peroxide, AOX, or ruthenium. So just what do you think will be the question? What do you think will be the answer? So in this entire case, so hydrogen peroxide is a byproduct of oxygen reaction. So when you have a byproduct, it cannot create any like variability. So hydrogen peroxide is out of question. So AOX is an enzyme. So basically that will be in the specific quantity. Whenever a designer is designing it, the enzyme AOX will be of a fixed quantity is what you will get. So that you cannot actually like that cannot be a source of variability in the sensor basically, because it is also not causing any since it and another factor is AOX is not having any redox reaction byproduct per se in this entire reaction. So AOX is not a source of variability. Ruthenium basically is a redox like it's a intermediary. Basically it is trans the more the amount of GPDH, there will be more the oxidation of ruthenium, and there will be more electron transfer. But the amount the amount of ruthenium or the what ruthenium does, the action done by ruthenium will always correspond to the amount of GPDH in the system. So the only source of variability in this, because because of the because how it slows down the ruthenium reaction, and it is not a byproduct of any antibody kind of reactions, is oxygen. So the source of variability in this, so variability is basically what is changing the electron transfer, or how it is affecting the electron transfer. The only component in the system that is affecting the electron transfer is oxygen. So the answer is oxygen. So do you understand it, or should I explain it again? So I think everyone has understood. So I'll just move to the next question. So again, they are asking what is the reaction happening between the indium tin oxide, ruthenium, and GPDH4. So this is one of the most simple questions. So I would request you to answer this question. So whether it is ECC, CC, ECC redox reaction, CC redox reaction, antibody antigen reaction, or proximity dependent reaction. So I would recommend, I would actually wait for you to answer. So I'll just wait for 2 minutes, and so that you guys can answer. So it's a very easy question. So please, I would like you to answer. I have given you hints previously. What so which is to give you a hint, in CC chemical reaction there is no electron transfer. In antibody antigen reaction there is no electron transfer, and in the proximity dependent reaction there can be electron transfer, but in this case the speed of the reaction is not due to so you can see there is fast and slow return. That is not because of the proximity, but that is because of oxygen, as I explained it earlier. So I would like you to give your answer. Great. So yes, the answer is option A. So basically, as I said, ECC and CC both are redox reaction, but in CC chemical there is no electron transfer happening. In electrochemical there is electron transfer happening. So here we can see electrochemical reaction is happening at the surface, and the chemical reaction is happening at the between ruthenium and GPDH. So that is the chemical electrochemical so electrochemical chemical system. So antibody antigen, that is not what is happening between the indium tin oxide surface, ruthenium, and CPDH. That is something which is happening between tropovin 1 and immunoglobulin antibody. That is not so that you need to understand that. Proximity dependent reaction, as I said earlier, it is here the electron transfer is not happening because of the redox cycling, and why it is slow and fast is not because of the distance, but it is because of the oxygen content in the sensor. So I think this was easy to understand. So let's move to the next question. So basically, what is not the role of nanoparticles in biosensors? To increase the surface area of reaction, to provide functional group for modification of biosensors, to improve ECC current, and to improve the signal to background ratio. So this is a very complicated question because nanoparticles. Um, you may have been through the previous weeks. You may have seen the nanoparticle being used for all most of these activities. So one thing is basically nanoparticle something, but here what we are asking is what is the role, what nanoparticle, what is the nanoparticle used for. So whether it is used for surface area of reaction, whether it is used to provide functional group for modification of biosensors, whether it is used for ECC, improve ECC current, and whether it is used to improve signal to background ratio. So let's take one by one. So nanoparticles, the main primary use of nanoparticle is to increase the surface area of reaction. Basically, why things change at the nanoscale is basically because there is a very high surface to volume ratio. So that is why you see the phenomenons at nanoscale which cannot be seen at micro or mesoscale. So answer 1 is surely the role of nanoparticles. So let's move to the second thing. So to provide functional group for modification of biosensors. So basically this has been done in many of the examples in the previous week. You have gold nanoparticles, you put NaBH4, you pre-treat it, with surface NaBH4, then you put some put some coating, and then you put the function. So you put the OH functional group using NaBH4 and those things. So that has been done very widely in the previous weeks. So the third, improve the ECC current. So basically, nanoparticles basically enhance the electrocatalytic activity of the reaction. So yes, it does improve the ECC current. So moving to improve the signal to background ratio. So basically what is happening is, in the nanoparticles basically just lead to a redox reaction. So basically nanoparticles, if you do if you only have a nanoparticles which is not taking part in any redox reaction, it will not enhance the signal to background ratio. Only if your nanoparticle acting as a labeling body taking part in a redox reaction it will increase the signal to background ratio, because that will improve the electron transfer rate. So from this you know what the answer will be. So the answer is option D, improve the signal to background ratio. So as I said, all these functions nanoparticle does on its own. In the last one, the nanoparticles are being used to improve signal to background ratio, but they are used as a as a tool in redox reaction. So if you don't have a redox reaction, or if you don't plan a redox reaction involving a nanoparticle, it won't happen. So it won't improve your signal to background ratio. Just if you just put a gold nanoparticle, it won't improve your signal to background ratio. It will just do the labeling part. It will label the antibody, secondary antibody, but it will not improve the signal to background ratio. That will improve only if you put, or if you design a redox reaction with centered around a nanoparticle. Then and only then you can use nanoparticles for improving signal to background ratio. So I think I am clear with my answer, or clear with my explanation. So moving to the next question. So yeah, so this is a very theoretical question. So calculate the limit of detection from the above graph with standard deviation of 0 data to be 0.1. So whether it's 0.1, 0.2, 0.3, 0.4. So basically limit of detection, the simple formula is 3 into standard deviation. So it's 0.3. So it's a formula driven, so I forgot to put the formula here, but I'll just put here in the chat. So the answer is C. It's a basic formula, 3 into standard deviation, limit of detection. So any questions? Okay, so let's move to the last question. So what can be achieved on PCB biosensing devices? Microfluidics integration, electrochemical measurement circuit, biosensing, all of the above. So this is basically a very simple question. This is for you to improve your marks. These kind of questions. So so basically in printed circuit board biosensing devices. Basically, we have printed circuit board. So printed circuit board, from the name itself, you know that you can do electrochemical measurement with that. So biosensing, obviously you can have a biosensor. Biosensor is basically you have a biological antibody, biological sensing elements such as protein, antibody, DNA, etc., enzymes, etc., and then you do the biosensing. So and the microfluidics integration, obviously you can do it. You can so a major example of PCB kind of biosensing device is the glucose sensor. So in this, what is happening is you have blood, a limited volume of blood is actually going through it. So microfluidics basically is where the volumes are in the microliter domain. So because the volumes are in microliter domain, it is easier to you can get a laminar flow in the setup. So then you can phase separation becomes also very easy. So you can separate the phases from. So if you have take a blood per se, and if you have a microfluidic device, and if you design it to be long enough, what will happen is your RBCs, the WBCs, and the other components will actually separate out depending on their weight. So basically the heavier will settle down and the lighter will move upward, and you can actually see the phase separation that can occur in the microfluidics. So in your glucose sensor, obviously you are having a microfluidics integration. So something which has been done with PCB biosensing, so something which everyone knows this is possible. Electrochemical measurement circuit. So when you are having a PCB printed circuit board, you are doing electrochemistry for measurement circuit is what electrochemical measurement circuit is what you actually plan to use it for. So that is a given, and it can also be used for biosensing. So this is the answer. Answer is all of the above. So yeah. So with this, we have completed this week's practice assignment. Do you have any questions? So these are there were 3 complicated circuits. So if you didn't understand any one of them, please tell me. If you want me to explain them again, I'll do that as well. So the questions are other questions are quite easy. So if you have any questions regarding the circuit or how the working is happening, just ask me whether you have any questions with that. Any questions? In case you don't have any questions, you are free to leave the session. I'll be just be or if you want me to revise all the questions again, all the circuits again, please let me know. In case you don't have any questions, just feel free to uh, leave the session. So just once again, I'll just go through the three setups. So yeah, so this is the first setup. So in this you have an indium tin oxide substrate. Then you activate the surface. So basically you have a flat surface. You want to activate it. Obviously, if the surface activation is not happening, you cannot do any coating on that surface. So first what you do is activate the surface. So you introduce polar groups on the surface by using aptase. So then after the aptase are done, you modify the polar groups, the amine groups basically, which are polar in nature, and you modify them in presence of with ferrocyanine carboxyaldehyde in presence of NaBH4. You do that, then you make the site ready to deposit streptavidin. Streptavidin is a heavy protein that is used basically because it has very high affinity towards biotin. It has 4 binding sites for biotin. So basically, since what your antibody here is a biotin fatted antibody, that is why you are using streptavidin. So understand that also. Understand why the person is using streptavidin. So he activated the surface, he functionalized the surface, he put the antibody, he put the protein so that he can put his specific biotin fatted antibody. He deposits streptavidin, he deposits the antibody, he gets the target antibody there. Then he gets the secondary antibody with ALP, labeled with ALP. So here ALP is a labeling element which is obviously supposed to take part in a redox reaction that will increase the signal to background ratio. So this is how the first sensor is working. So you have to understand why he is doing each and every step. So aptase he is doing so that he can do the further coating. So he has to activate the surface so that he can get the coatings done. Else if the surface is not activated, the coatings will not actually adhere to the surface. So that is why he's making the activating the surface, then he's functionalizing the activated surface so that he can deposit what that designer wants to deposit. Then he's depositing streptavidin because his antibody has is biotin fatted. So basically the streptavidin and the antibody has a relation, and then he's getting his target antibody, and then he's using a secondary labeled antibody that is supposed to take part in the redox reaction and increase the electron transfer rate. So this is the first setup. So this the second setup. So in the second setup, this is a quite a simple setup. So basically what is happening is you have a surface indium tin oxide surface, then you have an aptamer. Aptamer is a long protein chain. So then the toxin is being incubated. So what is happening is the toxin just goes and attaches to the specific area where it has very high affinity. It is attaching to that aptamer. So what is happening is because of that the electroactive probe is coming closer to the surface, and because it is coming closer to the surface, the electron transfer rate is increasing, and that is how the sensing is happening. So that is how the current you can see the current the intensity is increasing when the electroactive probe is coming closer to the surface. So that is what happens in the second setup. So in the third setup, so this is a very simple setup if you actually look at it. So you are using indium tin oxide substrate again. Then you use avidin because it is mainly used as a substrate for immunoglobulin antibody. So then you deposit immunoglobulin antibody. Then troponin 1 is what the antigen is or what the analyte is you want to detect. Then you have a immunoglobulin secondary antibody labeled with GPDH4. Then for the redox reaction, you have ruthenium in the setup, and plus you have AOX enzyme in the mix. So this is what the second setup. This is what the third setup looks like. So I hope all the three setups are clear. So anyone has any questions? So I'll just again, since people have joined in now, I'll just explain the setups again. I will not. You can look through the answers when I'm explaining the setup, but I'll just explain the setups because understanding the setup will give you an idea about everything. So I'll just start with the what the setup is doing. So you have an Indian plain oxide substrate. You are activating the substrate. You are getting your desired polar groups by using aptase. So you are just increasing the surface activity of the electrode surface using aptase. Then is when you are, since after you have got the activated the surface, you functionalize the functional group that are on the surface using ferrocyanine carboxyaldehyde and NaBH4 in presence of NaBH4. Then you deposit streptavidin. So why you deposit streptavidin is because your antibody, which is the primary detection antibody, is fatted with biotin, and streptavidin has 4 biotin binding sites. So understanding it, so activating the surface, activating the functional group on the surface, then putting streptavidin because that has very high affinity to your primary antibody, then depositing your primary antibody, then getting your target antibody, and after you get the target antibody, you put a labeled secondary antibody. So labeled secondary antibody is supposed to, basically it is supposed to take part, because it is labeled with ALP, it is supposed to take part in a redox reaction, and that will in a way enhance the electron transfer rate, which will improve the signal to background ratio. So that is how it is happening. So this is the first question: what is the role of NaBH4? So the, as I explained it, it is functionalization of surface absorb aptase. Then the second question: what can be the RCT change due to streptavidin? As I said, streptavidin is a very high weight protein. So because of the very high weight, the what will happen is the charge transfer will be slower, because it will, the higher the weight of the protein, there will be more resistance to the electron flow that will be happening. So that is why the charge transfer reaction will increase. Then the third question: so what is the role of secondary antibody? As I said, it is labeled with ALP so that it will take part in redox reaction, and that is why it is that is what its function is, to improve the signal to background ratio. Moving to the next setup. So here what is happening is you have an indium tin oxide substrate, then it is attached with the aptamer. So they might have done surface functionalization and other things, but that is something which is not our concern now. So in this setup we have aptamer. So aptamer is basically long chain proteins which has numerous binding sites, hundreds of binding sites. So then it is attached to electroactive probe. So what is happening is, when you are incubating in toxin will find out its specific binding sites in that aptamer, so that, and then it will attach. So that is causing the aptamer to curl around the toxin, and then what is happening is the electroactive probe is coming nearer to the substrate, so that is leading to faster electron transfer. So that is why you can see higher current, bound current in the, when the electroactive probe is coming near to the substrate. So coming to the question, what is the concept used? So basically, it is used as proximity dependent electrochemical reaction. So it is the proximity is changing, and the current what you are detecting is changing. So that is the first question. And the second question, as I said, it's aptamer. It is a long chain protein which has numerous binding sites. So now coming to the third setup. Third setup, basically this is um, Indian tin oxide substrate. It has avidin. It has avidin will be attached to immunoglobulin antibody, because avidin has high affinity to immunoglobulin. Troponin is the analyte or antigen, whatever you can choose. Then you have a secondary immunoglobulin antibody labeled with GPDH. There are two. There is one there is one enzyme AOX. Then there is a redox reaction happening, that is between. So GP is converting. Is being oxidized by GPDH4, which is leading to reduction of oxidation of ruthenium, which again reacts with indium tin oxide and leads to electron transfer. Here in the second case, the same reaction is happening slowly, because oxygen is taking away all like oxygen so when you have a specific number of electrons that are available, what is happening is oxygen is taking up all the electrons in a faster speed compared to ruthenium. So that is why oxygen is then converting to H2O2. So that is how the reaction is happening. So here you have the source of variability in this sensor is oxygen. In the and the second question what they are asking is, in the seventh question, what is the type of reaction happening between the Indian tin oxide surface, ruthenium, and GPDH4? So basically, it is a redox reaction with electron transfer. So it cannot be a CC redox reaction. So it has to be a ECC redox reaction. So yeah, now coming to the eighth question, what is not the role of nanoparticles in biosensor? To increase the surface area of reaction, to provide functional groups for modification of biosensors, to improve ECC current, and to third, the last option is to improve the signal to background ratio. So the answer is to improve the signal to background ratio. So basically, all you might see many examples where gold nanoparticles are used to improve the signal to background ratio, but that is happening only when there is a redox reaction that is designed with the gold nanoparticle or the activated gold nanoparticle inside, or coated gold nanoparticle. So that is not what, if you just put a nanoparticle labeled with a gold nanoparticle, that will if you put a secondary antibody labeled with a gold nanoparticle, that will not improve the signal to background ratio. You have to design a redox reaction around it, so that you can actually improve the signal to background ratio of a biosensor. So that is what the understanding behind this question is. So this is a very formula based question. So basically the graph is actually of no use. You just have to calculate the limit of detection for the above graph with standard deviation of zero data to be 0.1. So basically the formula for standard deviation is 3 into the formula for limit of detection is 3 into 3 into standard deviation, so that is 0.3. So now coming to the last question. So what can be achieved on PCB biosensing devices? Microfluidic integration, electrochemical measurement circuit, biosensing, all of the above. So it's a printed circuit board, a biosensing device. So you can understand that all the both B and C is given. So now coming to microfluidics integration, basically using microfluidics is very easy. You can even have micro needles, which we had in the previous week also. So microfluidic integration is quite easy. One of the basic example of PCB based biosensing device is a glucose sensor. So the answer is all of the above. So any questions? Those who came in now, any questions? So any questions? I have gone through the setups again. So if you have any questions, please let me know. I don't see anyone attending the call. So I would just like to thank you for your attention, and I will see you next week.